Okay, so what is the guideline? Okay, so curve sketching. The guideline, the first step of the guideline is that once we're given a function, okay, we sketch a curve of a function. So f is a function. This function, we're gonna first work out the domain, right? Domain, range, etc. B, the second step is usually about intercepts. Intercepts include y-intercepts, x-intercepts. These are the things we've done in our previous algebra classes anyway, okay? So we're gonna do the intercepts. So that means intercept, y-intercept, okay? Y-intercept and x-intercept. X-intercepts, it could be plural. And C is about symmetry. Whether the curve is symmetrical with respect to y-axis. If it is symmetrical with respect to y-axis, that's the kind of function we call even function. If we have an even function, we'll only have to graph half the curve, and the other half is just a reflection over the y-axis. So we will check if the function is even, right? Even function, right? We know that for even function, for opposite input, right? When the input are opposite and their output are the same. That this is true for all the axes in the domain. So in this case, we only have to graph half of the function in the domain. And odd function, right? Odd function, and we certainly have learned these before. Odd function is that when the inputs are opposite, right? We have output here, and we have another output, right? So the input are opposites. You see, the input are opposite, and the output are opposite as well. Okay, so this is what it means. Opposite input produces opposite output, and this is also true for all the functions in the domain. And the curve is symmetrical with respect to the origin. So in that case, we can also take advantage of the situation. We know the basic functions such as sine is odd, cosine is even, x squared function is even, x to the power 3 function is odd, but those are basic simple functions. And we will be dealing with much more complicated functions. Okay, D is we're going to study the asymptotes. The asymptotes will include the vertical asymptote and the horizontal asymptote. Okay, and these will allow us to apply what we learned in calculus. Okay, so for vertical asymptote and horizontal asymptote, right? In the horizontal asymptote, what are the relevant calculus concepts? For horizontal asymptote, right, for horizontal asymptote, we will be studying limits of the function as x approaching positive infinity, f of x, right? And we will also be studying this limit as x approaching negative infinity. So this will help us to find the horizontal asymptote. Okay, and the vertical asymptote. Vertical asymptote will be the cases that we get to use. Oh, whoops. For the vertical asymptote, we'll get to use the calculus concept. Okay, we will be studying the limits, but not as if x approaching a specific number from right, from left, or from both sides, right? So we'll be studying these limits. Okay, if we study these limits, and these limits, if this equals to infinity, or this equals to, it could be positive infinity or negative infinity, right? Hold on. It could be negative infinity. It could be, so these cases will be the cases where we'll be observing if we have these, we got vertical asymptotes. Okay. These cases. So you can see ABC, we know how to do it before we take calculus class. For asymptotes, we have done it before for vertical asymptote and horizontal asymptote without the calculus tool. So now we have the calculus tool, so we can use the calculus tool to do the asymptotes. And the next few will be what we have learned recently, which is use derivative to discover the interval of increasing or decreasing, right? And F will be, we can find local max or local min using first derivative test. Okay, local max, local min, and G, we can certainly use second derivative test, right? And concavity using second derivative and point of inflection, right? So we've learned these concepts before, well, recently. And last but not least, we can sketch the curve. We are not excluding the use of technology in this case, okay? Because in today's time, graphing calculator are convenient. Well, they're convenient tools, and it helps us to see the curve. However, these analytical tools are also necessary to help us to see better about the curve, especially what to look for. Okay, because oftentimes, no matter how sophisticated the graphing tool is, it always have details that we need to analyze using these analytical tools. Okay, so let's take some examples. Okay, one of the first one would be, I'm going to use some of these examples that are, we start from relatively easy to involve a different kind of functions. For example, we're not going to be just using polynomial. We're going to be using rational functions. We're going to be using some exponential functions, and we might be using some trig functions, right? So we will get to use these functions that we have learned before to see how we can explore, all of these items from A to H. Okay, so let's get started. This example I'm going to use is actually from the textbook, edition number 8. Okay, and I call this example number 1. The function in consideration is f of x equals to 2 times x squared divided by x squared minus 1. Okay, so we're going to go through all of these items. We're going to go through all of these items. Okay, so I'm going to put all of these items here as our guideline. Okay, step 1, domain. And in our case, this is a rational function. So the domain, the denominator cannot be 0. Right? As a result, we found that x cannot be positive 1 or negative 1. It cannot be positive 1 or negative 1. Negative 1, that's it. Now, intercept. It's easiest to find the y-intercept, right? Y-intercept where is the input equal to 0. So when x equal to 0, right? So we first find y-intercept. We tell the reader what I'm doing here, right? We set x equals 0, so replace x by 0, replace x by 0, so the y-intercept is 0, 0. And x-intercept, right? Well, we might have more than one, and we're gonna set it equals to, we're gonna set the function equal to 0 because x-intercept is where the curve crosses the x-axis. So we're gonna set f of x equals to 0. We're gonna set f of x equals 0. If f of x equal to 0, denominator cannot be 0. The numerator has to be 0. So x squared has to be 0. 2 cannot be 0, right? 2 cannot be 0. So x squared is 0. If x squared is 0, x must be 0. So the x-intercept, it turned out to be 0, 0 as well. X-intercept and y-intercept are the same. Okay, symmetry. Symmetry, we mainly check with even function or odd function, right? So what do we have here? We're check whether it's even function, we're going to replace x by negative x. Okay, so x is replaced by negative x. And we simplify. Negative x squared is the same as x squared. Negative x squared is the same as x squared. So when the input are opposite, the output are the same. So this function is, the curve is going to be symmetrical with respect to y-axis. Okay, so symmetry about y-axis. And if it is an even function, it's not odd function, right? So in this case, we got even function asymptote. We do have some vertical asymptote here. Okay, so let's first look at vertical asymptote, and then we're going to look at horizontal asymptote. Okay, so I'm going to put a horizontal asymptote under, and we're going to observe vertical asymptote. Vertical asymptote, in our case, we're going to think about what are the numbers that cannot be in the domain. So the function is as such, right? And if we factor the denominator the denominator is factored into the product of x minus 2 times x plus 1 times x minus 1. As you can see, right, the numerator is always positive, right? So depending on when we approach, so we're going to observe some limits. Okay, so because 1 is not in the domain, so let's look at the neighborhood of 1. Let's look at the neighborhood of 1. So a becomes 1. So we're going to observe these two limits. Okay, we're going to observe these limits. For positive 1, left and right, when we approach 1 from larger than 1 on this limit, okay, so let's write it up. Let's see how we analyze it. Okay, so this is the function, right? So the way I'm going to write it is that as x approaching 1, the numerator is going to approach a finite number. The denominator is going to approach 0. Okay, but if x is larger than 1, this is going to be positive. And this is going to be positive, right? So this whole thing is going to approaching positive infinity. Okay. The denominator, when we approach 1 from smaller than 1, okay, what you can do is that you see this piece as when x is approaching 1 from smaller than 1, then this piece becomes negative. The rest of the piece is positive. So the limit is going to be negative infinity. So we have vertical asymptote at 1. Okay. How about negative 1? Right? Why do we also consider negative 1? Because negative 1 is not in the domain, right? So for negative 1 from greater than negative 1, larger than negative 1, right? So we consider this limit, right? So we don't know the answer yet. When we approach negative 1 from larger than negative 1, then this piece, well, this is going to be positive anyway, but we approaching x from larger than negative 1, so this piece is negative. So this piece and this piece together makes negative. When x is approaching negative 1 from larger than negative 1, okay, this piece is positive. Positive, negative, positive, so this is going to be negative infinity. Okay. If you need time to think about it, don't hesitate to pause. Okay, it's a matter of sign, right? You can also view this as, just use sign notation. Just use sign. When x is approaching negative 1, right? This piece is a negative, positive. So this together is negative. And this piece as x approaching negative 1 from larger than negative 1. If it's larger than negative 1, you're thinking of negative 0.9, negative 0.99. So this piece is positive. So the whole thing is negative. That's why approaching negative infinity. And this other one, okay, this is still negative, but x is approaching negative 1 from smaller than negative 1. So you're thinking of x might be like negative 1.01, so on and so forth. This piece is going to be negative. So negative times negative is going to be positive. So this is going to be approaching positive. So we got two vertical asymptote. One is positive 1 and the other one is negative 1. Okay. So we got vertical asymptotes. And they are x equals to +1 and x equals to -1. Okay, so these is explained by first two and the next two. Okay, so we have two vertical asymptote. So let's look at the horizontal asymptote. Horizontal asymptote is that we observe the limit as x approaching +infinity or -infinity. Okay, so we have a function here. Okay, you can use any one you want. So we take limit as x is approaching +infinity. Okay, when x is approaching +infinity, we're taking this limit on this function. What we can do is that we can divide. We cannot use the limit law because as x approaching infinity, the top approaches infinity, the bottom approaches infinity. It's the infinity over infinity case. So we cannot use the limit law until if we have, individual limits exist, right? So the top will divide it by x squared. So we have 2, right? The bottom divided by x squared. So it's a 1 minus 1 over x squared. I hope you understand what I did here. What I did here is I divide the top. Okay, so let me insert another step. I divide this piece by x squared. Okay, divide this piece by x squared. There's a common technique we used before when we were in the limit session. Because x is approaching infinity, so we can assume x is a very large number, positive. So we can divide x squared by on the top and x squared by the bottom. Basically, we apply principle number 1. So we ended up with something like this. So now each individually exists. This 2 is a constant, 1 is a constant. This piece has a limit 0 as x approaching infinity. So this limit is 2. Okay. Then you say, what if we approach negative infinity? When we approach negative infinity, right? We actually can play the same trick, same thing, right? In fact, because we have x squared, all of these can be repeated. All of these can be repeated if negative infinity is what x approaches to. Okay, all of these works. So we could have just we don't have to do even this part because the limit is the same. And this tells us we have a horizontal asymptote. And this horizontal asymptote is y equals to 2. Okay, so we get a horizontal asymptote here. That's it, right? So you can see all of these, the first few items we did here, A, B, C, D, are things we've done before and we could do before we took calculus class. And now with the calculus tool, we just have more tools, right? But the idea is the same. Okay, we can remove these if you wish. Okay, we don't really need these. These are they're just from the guideline. Okay, so now this is nice and cleaner. So next is the part we've done recently. Okay, using the first derivative tool to find the interval of increasing and decreasing. Okay, so in order to identify the interval of increasing, decreasing, of course, we have this function and we know all about E and F. We can think of them together. So we're going to take a derivative. Quotient rule. Okay, so x squared minus 1, then squared, quotient rule, and f prime. So the function on the top, 2x squared, the derivative is 4 times x, multiply x squared. Subtracting now 2x squared, the derivative of x squared minus 1 is 2x. Right, so simplify, I can factor out the 2x here, right? So on my next step, I can simplify, I can put it this way, and bring out the 2x, and 2x is brought out. I'll have 2 left, so 2x is out. This way, inside the parentheses, 2 times x squared minus 2, so we have 2x squared minus 2. And we ended up with 2x times negative 2. So in the end, we have these 2 pieces are gone. So we just have negative 4x right there. So now we are interested in the interval of increasing, decreasing, right? And what kind of situation is that? Denominator is always positive. Numerator, we have a negative 4x. So when x is positive, negative 4x will be negative, right? When x is negative, negative 4x will be positive. So this way we can tell when x is negative, right? X is negative times negative 4, that's positive. The derivative of the function is going to be negative. So that tells us f is decreasing, is decreasing, sorry, is decreasing. No, wait, when x is negative, this is a positive, my bad. Okay, so f is increasing. But in this case, make sure x cannot be equals to negative 1. Negative 1 is not in the domain, right? Now, so there are 2 intervals in the case of x minus 1, right? So f is increasing. F is increasing in these 2 intervals, okay? Negative infinity to negative 1, oops, negative 1. And another interval will be from negative 1 to 0. There. And increasing wise, oops, for increasing wise, when x is positive, right? The derivative is going to be negative, right? For x, this is positive. Positive times negative 4 is negative. So this is a negative. In this case, f is decreasing. But since x equals to 1 is in this interval, right? So x cannot equals to 1, then we will say f is decreasing, right? F is decreasing on the interval of 0 to 1 and 1 to infinity. So we have discovered the interval of increasing and decreasing. Let's look at local max, local min. Okay, let's look at local max, local min. Well, at a positive 1, negative 1, the function goes to infinity. So we're not going to, they're not differentiable at those positive 1, negative 1. Okay, and we're not going to have local max, local min there either, because they're approaching, if the value of the function approaches infinity. So the only critical number we need to consider is x equal to 0, right? So the critical number C is equal to 0, because that's what, when you set a derivative equal to 0, right? We set f of x, the derivative of the function equals to 0, right? So we get x equal to 0. So this piece equal to 0. Denominator cannot be 0, so x must be 0. So that's the only critical number, right? So that's the critical number. Before 0, right? Before 0, when x is less than 0, the derivative is positive, which is increasing, right? When x is negative, the derivative is decreasing. The derivative is negative, the function is decreasing. So we're using first derivative test. So by first derivative test, right? F has local max or min. I pause. Increasing, decreasing, right? We have a local max at 0. And what is the local max value? Well, the local max value can be found at 0, but x replaced by 0, but one f is 0, when input is 0, output is 0. So that's the local max. Concavity. Okay, for concavity, we're almost done, right? We have to find second order derivative. We already have the first order derivative, right? We have the first order derivative. And we just remove that part. We keep it simple. Let's find second order derivative. When we try to do that, we might want to leave the negative 4 outside, right? So we just find derivative of that part. So find derivative of that part. It's just make it a little simpler. So derivative of the first order derivative, we have the negative 4 outside, and we differentiate that part. Okay, so the quotient rule again. So the denominator is going to be squared again. So this is going to be power 4. Derivative of x is 1 times the denominator. Subtracting. Okay, we keep the numerator, take a derivative of the denominator. We're going to use the chain rule. So that's going to be 2 times x squared minus 1. And then we differentiate x squared minus 1. That's going to be 2x. Chain rule. Okay, so let's simplify. Okay, so negative 1 times that. And over here, this is 2x. So this is going to make it 4x squared. Okay, so this piece gets removed, right? 2x is 4x squared. what I'm going to do is I'm going to factor out the x squared minus 1. I'm going to factor this out. So there's only one of them left there. Okay, feel free to pause this part and do your own algebra. Now, this x squared minus 1 and x squared minus 1 in the bottom can be reduced. So the next step, right? So this piece will take away one of these on the bottom. So this will be 3. And on here, we have x squared minus 1. We opened up the parentheses. So this is x squared minus 4x squared. So this is 3. Right? And this piece, we can factor out the negative sign. So 1 plus 3x squared. And this negative sign and that negative sign makes positive. And remove that parentheses. There we go. We got it. Once we have this form of second order derivative, and we want to assess the sign of the second order derivative, the top is the numerator is always positive. The numerator is positive. Okay. What will change sign? The denominator could change sign because the denominator is x squared minus 1 raised to the power of 3 is an odd number. So when the parentheses is positive, the denominator is positive. When the parentheses is negative, the denominator will be negative, right? So you can write this as this form. Put it this way. So the whole of the numerator is positive. The whole of the numerator is positive. The denominator may have change of sign. So let's study the sign change of the second order derivative. Okay, we know that positive 1, negative 1 cannot be. Well, first of all, there will be no number that will make the second order derivative equals to 0. Okay, so we're going to study concavity. And are we going to have an inflection point? Is there a place that we have a change of concavity? Well, if we set the second order derivative equal to 0, we have no solution. We have no solution. So there's no concavity point. Okay, so the only thing is we have to observe the sign. Okay, so the sign is determined, as we said, by x squared minus 1, right? So how the sign changes for x squared minus 1? X squared minus 1. One is it negative, right? If this is negative, what does that mean? That means x squared is less than 1, right? And the absolute value of x is less than 1. In other words, if x is between negative 1 and positive 1, in this interval, the derivative, second order derivative is negative. Okay, so that is, okay, when x is in this interval, right? Second order derivative, which is this piece, right? The denominator is negative, so the whole thing is negative, which is concave down. Therefore, on the other hand, less than -1, right? So on the interval from -infinity to -1, right? Or from 1 to positive infinity when x is on these intervals, right? i.e., when x is less than -1, or x is larger than +1. In these cases, the second order derivative, in this case, right, x squared minus 1 will be positive. And that's a concave up. Concave up. So concavity is studied. Okay, concavity is studied. Next, right, we have no inflection point, right? So because we said second when we said second order derivative equal to 0, right? No solution. No solution. So no point of inflection. So last but not least, we're going to sketch the curve. We're going to put all of these things together. And of course, we can use some graphing tools. Okay, we can use some graphing tools to do this. So now we're going to bring our functions with us. This is our function. You could have sketched it a little earlier before, right? So let's look at the curve. There. Okay, I'm gonna make some adjustment. Looks like there's some more stuff. Let's see, -5 plus 5. Right? We're gonna put more things in place. Okay. So what are the more things? Horizontal asymptote. Horizontal asymptote. We have a 2. Y equals to 2 is our horizontal asymptote. Okay, so we're going to make that. What color would you want it to be? Make it maybe green. Broken line. That's horizontal asymptote. We have 2 vertical asymptotes. Okay, 1 vertical asymptote. We're going to make it red. Broken. Another vertical asymptote. 2 vertical asymptote. Concavity. We certainly saw concavity between -1 and +1 is concave down, and these 2 other pieces is concave up, right? So that agrees with our analysis. And I think that's all. That's all we have for this question. And that's our first example. That's our first example. And I think I'll make another recording to do another example. Okay. Thank you for watching. If you have any questions, please feel free to ask me. And you can try some questions. So what I plan to do is that these, even though we're not going to have lessons in class, in the classroom, in person to do these, but I may have questions asked on the final exam as extra credit. Okay, so on curve sketching. So thank you for watching.